Okay. So good evening all of you. So today we will discuss the topic of classical mechanics, which is one of the most important and easy topic for the lecture CADRE physics examination. Okay. 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 So today's topic is Lagrangian dynamics. Okay. So we know that in mechanics we have Newton's laws of motion to describe the dynamics of the particle. Okay. So whenever we have to define something, whenever we have to describe the dynamics of the particle, we need some coordinates to specify the position of the particle. For example, here is x, here is y, here is z. Okay. So if I want to study the motion of this particle, let us suppose this is a particle at a point P, and I want to represent the point of this particle. Okay. So what is the in Cartesian coordinate, the coordinate are x, y, z. Okay. That is a position along x axis, position along y axis, and coordinate of position along the z direction. Okay. And similarly in spherical coordinate system, the coordinates are r, theta, phi. Okay. And in cylindrical, the coordinate are rho, phi, z. Okay. So because to describe the motion of the object, we need the position, initial position, as well as the initial velocity of the particle. Okay. So if I have one particle which has an initial velocity something, for example 10 meter per second, and I want to know that what will be the position and velocity of that particle after some time. Okay. So I have to describe that from where particle is started and from where and what was their initial velocity. Okay. So before going to the Lagrangian dynamics, first we have take few minutes to describe or to state some basic concepts or some terms which we'll use later on. So first term is generalized coordinates. Generalized coordinates which we represent by qi. Okay. So because if there is a one particle, so we have to only qi. Okay. So if we have a one coordinate, then that is a q, for example x, but because there is a general coordinate that x, y, z, and in n dimension we need n coordinates. Okay. So that is the reason we will take here is the index I to represent the discrete number of the or many body problem. Okay. So what are the generalized coordinate to specify the state of a system, we need some variables. Okay. Variable are called, which are called generalized coordinate. Generalized coordinates. Okay. Okay. So we represent these generalized coordinate as qi. Okay. For example, qi, that I will take from the 1, 2, 3. In 3 dimension, I will be equal to 1, 2, and 3. Okay. So for example, q1 will equal to x in Cartesian coordinate, q2 will equal to y, and q3 will be equal to z. Okay. Okay. So we have a choice of the choice of the coordinates. We can use Cartesian coordinate, we can also use the spherical coordinate, and we can also use cylindrical coordinate. Okay, but what we are doing in this, because we are formulation some new approach to study the motion, so we have to generalize these coordinates. Okay, and we called it as qi. Okay, so qi can be x, y, z, r, theta, phi, rho, phi, z, and another coordinates. Okay, so these are the variable. So general coordinates are the variable. For example, in thermodynamics, we can take the example of thermodynamics. In thermodynamics, the state of system can be described by the PVT. So PVT, pressure, volume, and temperature, are also the generalized coordinate. Okay. Okay. So let's take example. Of generalized coordinate, that is pendulum. Okay, example of pendulum. So for example, we have a pendulum. Example of pendulum. Okay, so let us suppose here is pendulum. Okay, so have bob, pendulum of bob having mass m, and the length of this pendulum is L. Okay, and this length is in making angle theta. Okay, so if I have taken, let us suppose these are the coordinate system, x and y. Okay, so these are the coordinate system, here the origin x and y, and here is a system, that is a pendulum. So how will I represent the the state of this pendulum? Okay, so there are two ways. So what I can do, that this pendulum is moving like this. Okay, so let us to make more easy, let us take coordinate system. Let us take here origin. Okay, so origin at this point of suspension, and this coordinate is x and this coordinate as y. Correct? Okay, so here this distance will be equal to x, and this distance from origin to here, the position of pendulum is y. Okay, so here is the coordinate of this bob of the pendulum will equal to x and y in Cartesian coordinate. Okay, so we can write, by using the Pythagoras theorem, we can write this x square plus y square is equal to L square. Okay, so x square plus y square is equal to L square. So here these x and y are related by equation, this equation, and x here is, for example, y can be written in term of x because L is a constant. So x is a independent variable and y is a dependent variable. So y is depending upon the x. So let us take this as equation number 1. So this is the generalized coordinate. So generalized coordinate here is x and y. Q1 is x and Q2 is y. Okay, so to deal this system of pendulum with Cartesian coordinate system is little bit difficult, because we have to we need two coordinate. Okay, we have two variables. Okay, so equation of motion later on is difficult to solve for the two variables. So we can use another coordinate system, that is called the plane polar coordinate system. So here is a, for example, here is the position of pendulum at any instant. It is making angle theta. Here is length is L, and it is moving like this. So here in plane polar coordinate system, So what is the in plane polar coordinate system? That is, if we take here origin, then this distance is r. Okay, so r and the angle made by this pendulum with respect to this axis. Okay, so here is theta, r and theta. So because r is equal to L, here r is equal to L and theta. So L is a constant. So now because L is a constant, we have to deal only with one variable, and that is called the theta. So we have reduced the variable from two variables to one variable. So whenever we have to solve the problem of Lagrangian for the pendulum system of pendulum, we will always use the plane polar coordinate system. Okay, so correct. So now we can say that general coordinates, so from these two examples, equation number 1, here is actually L and R. Okay, okay, so from this, here is a X and L, here is L and theta in plane polar coordinate system. So generalized coordinates are not unique. Generalized coordinates are not unique, but independent generalized coordinate, independent generalized coordinates are unique. So in this pendulum, the choice of coordinate system is not unique. Okay, so we can use x, y, that's the Cartesian coordinate, or we can use the polar coordinates. Okay, but we can see here in Cartesian coordinate system also, there is only one independent variable, that is x, because y is depending upon x. Okay, and similarly in this plane polar coordinate system, there is only one independent variable, and that is theta. Okay, so that is the concept, most important concept, that general coordinates are not unique, but independent generalized coordinates are unique. Okay, so let us take another example to understand this concept more precisely, that how to choose, that is choice of coordinate system, choice of coordinate system, coordinate system. So let me take one example. Let us, we have a system. Okay, here is x, here is y, and I have a one inclined plane here, and we have placed here box on this inclined plane. Okay, and this plane, actually this inclined plane is moving along this direction. Okay, moving along the x direction, and this v, actually because this contact surface between this inclined plane and the block is not a frictionless, so there will be force on this block. Okay, so due to friction, this block will also move. So let us suppose that this block is moving in this direction. Okay, so now we have to choose, we have to describe the dynamics of this system. So we need some coordinate system, so we have to specify that what are the coordinate system. So let us choose here origin. Okay, so position of this block is, let us suppose x direction is x, okay, because this inclined plane is not moving along the y direction, it is only moving along the x direction, so we need only one coordinate, that is x, capital X. Okay, and this block is moving in a xy plane, this is moving in x direction as well as y direction. Okay, so we need here, let us suppose the coordinate, x coordinate of this block is small x. Okay, small x, and the y coordinate of this block is equal to small y, and let us suppose the inclination angle is alpha. Okay, and the length of this this length of this inclined plane base is equal to L. So L is constant, alpha is constant. So what are changing? That is X, capital X, X and Y. Okay. So let us suppose that we can find out this distance. This small distance from here to here is. So this is X minus capital X. X minus capital X. Okay. And here is, this distance is equal to, whole distance is equal to L, and we have to find out this distance from here to here. So this distance is equal to L minus this whole quantity, that is L minus X minus X. Okay, or we can write this as L minus X plus X. So to find out the relation between the coordinate system, what we will do, we will consider this triangle, this Y, this triangle. Let me take here in figure. Here is a triangle. It is making triangle like this. This base is L minus X plus X. Okay, and this Y, here is a that block. This Y is actually, this is Y, correct, and this angle is alpha. So from trigonometry we can use that tan alpha is equal to perpendicular upon both upon base, okay, P by B. So that is Y divided by L minus X plus X. Okay. So now from this equation we can find out the relation between the different coordinate systems. So here how much coordinate we need? 3 coordinate. X, capital X, small x and small y. So there is a 3 coordinates. We need to specify the position of this block and this block. 1 coordinate for this block and 2 for this small box. Okay. So these 3 coordinates, that x, y and x, they are related by some equation, and that is that this relation is equal to y is equal to tan alpha, okay, and multiply by L minus X plus X. So here we can say that independent coordinates are 2, x and x, okay, and y is a dependent coordinate because it is depending upon x, these two small x and capital X. Okay. So generalized coordinate, independent generalized coordinate are 2 here. Independent generalized coordinate 2, that is x, capital X. Okay, or we can change it either way. Okay, we can express x in terms of y and capital X in terms of y and x. That is our choice. Okay, so this is one method. This is one choice of coordinate system to define, to write down the. This is a one choice of the coordinate system for this system. Okay. Now there is another approach which is much easier. So what we should do actually, let us suppose here is a, this is x, this is y, here is origin, here is alpha, okay, and here is some that box. So what we will do actually, we choose coordinate system in a such a way that here this coordinate, we choose this as x, one coordinate here x and another coordinate here, that is, let us suppose s. Okay. So if box is here, so we, for this box we will take coordinate system like this. Here this is y and this as x. So here is a small x, this is small x. Okay. So if we take this as a coordinate system, then we have a complicated kind of the equation. Okay, and we have a 2 coordinate system. We have studied that, okay, in previous slide, that the generalized coordinate, the independent generalized coordinates are the unique. Okay, so we can use this variable or we can use this variable. Okay, so if we take coordinate system like this, then we have to need three coordinates. But if we use like this, two different coordinate system for the box and block, then we can use x and x. We measure distance of this box from here and the distance of position of this block from here, inclined plane actually from here. Okay, so now the next concept which is related to generalized coordinate is degree of freedom. Degree of freedom. Okay, so as name suggests that how much free a particle to move in the any direction. For example, let us suppose this is x, y and z. Okay, so if I have this particle here, one particle, so it is free to move in any direction. It can move along x axis, it can move along y axis, it can move along z axis or any direction. Okay, but if I have a two particle, for example, okay, and they are connected with here this. Okay, so let's take another example. If I have a one particle, let's take much more easier example. So this particle is free to move in any direction. Okay, but what happen if one particle is moving along a, here is a wire, circular wire, and here is a bead. So this bead can slide only in this circular path. Okay, so it is only free to move in this circular path. So how much freedom particle has to move in any direction? So that is layman language, what is the degree of freedom. Okay, so degree of freedom in mathematically, so definition of degree of freedom is minimum number of minimum number of independent generalized coordinates to describe the dynamics of a system. Dynamics of the system. Okay, so from this definition we can find out the degree of freedom of previous example which we have taken here. Okay, so for example, in case of pendulum, there is a one independent coordinate, that is theta. Okay, or in Cartesian coordinate, that is x. So degree of freedom here is 1 from definition. Okay, another, in this example there is a two independent coordinate which we can specify for the dynamics of the motion. So degree of freedom here will be 2. Okay, okay, describe the dynamics of the system. Okay, so mathematically we can write as degree of freedom is equal to number of coordinates, okay, minus number of constraint equation. Okay. So degree of freedom is equal to number of coordinates minus number of constraint equations. Okay. So for example, here, if we take the example of pendulum, okay, so here is a pendulum in plane polar coordinate system. Here is origin, here is theta, and here is L. So here is L into theta, and this is moving like this circular arc. And we know that in Cartesian coordinate this position is actually x, this is y. Okay. So constraint equation, constraint means the limit to the, it set the limit to the motion of object. Okay. So that x square plus y square is equal to L square. If we use Pythagoras theorem here to this triangle, then x square, okay, plus y square is equal to L square. So here constraint equation is only one. Constraint equation is equal to 1. Okay. And number of coordinates are equal to 2. Okay. X or y or L or theta. Okay. Because here L is equal to actually R. This is R. So in general case it will be R. But R is equal to L, it is constant. So here is number of coordinate will be 2. Okay. So degree of freedom will be equal to number of coordinates minus number of constraint equations. Okay. So that is equal to 2 minus 1. Also, okay, so this is, that is equal to 1. So from this equation we can also find out the what is the degree of freedom. Okay. So this is very simple case. Here we have also find the degree of freedom by the simple definition. That is also 1, and from this formula it is also coming out to be 1. Okay. So another formula, let us suppose if we have, okay, if we have, let us suppose if we have n number of particle, another definition of the degree of freedom, that is if we have n number of particles moving in d dimension, okay, d dimension, then degree of freedom will be equal to n number of particle d minus k, where k is a constraint equation. Yeah, number of constraint equation. Okay, that is correct. Number of constraint equation. So this is a formula of degree of freedom. Okay. So now let's take one example. Let us take another example to use this formula. Okay. So here is x coordinate, here is a y coordinate, and here is a z coordinate. Okay. So let us, this is a 3-dimensional space, and here is a 2 particle. Particle 1, particle 2, they are connected by this equation. Okay. So coordinate of here is x1, x1, y2. Okay. x1, y1, and z1. Here is x2, y2, and z2. Okay. And the distance between these 2 particles is L. Okay. So what is, to find out degree of freedom, we know that degree of freedom is equal to number of particle, okay, dimension, okay, minus k, that is number of constraint equation. So we have to find the constraint equation between these 2 points. So we know that if we have a 2 points, and if we want to find out the distance between these 2 points, so there is a distance formula. What is that distance formula? That is, for example, L. So L square is equal to L square is equal to, okay, difference between these, square of the difference between the corresponding coordinates, that is x2 minus x1 whole square plus plus y2 minus y1 whole square plus z2 minus z1 ka whole square. Okay, so here constraint equation is only one. There is no another equation which can be in which can relate these coordinates. Okay, there is only one choice. So now if we put these things in this equation, we use this, for example, this equation 1, use equation number 1. So degree of freedom, in this case number of particle are 2. Here is 1 particle and 2. Number of particle are 2. D is a dimension, so dimension 3 dimension, that x, y and z, 3, and constraint equation is 1, so that is minus 1. Okay, so 6 minus 1 is equal to 5. So there is a 5 ways, there is a 5 waves in which motion can be executed by these two particles. So what can be that? Either they can move along x-axis, okay, in this direction, y direction or z direction. Okay, so translation about 3 axis, so that is 3 degree of freedom. Okay, so translation degree of freedom will equal to 3. Okay, or 2 degree of freedom are rotational. So because these particles are along the x-axis, okay, so these can be rotate about the y or z axis, but it cannot rotate about the x, and it can rotate about the x and z axis, but it cannot rotate about the y axis. Okay, so that is concept of the that is the concept of the moment of inertia. Okay, so rotational degree of freedom R2. Okay, so this is one example from that how we can use this formula to calculate the degree of freedom. Okay, so I have given to calculate the degree of freedom, there is a 3 way. Okay, one is by definition. If the system is simple, so we can use simply definition, and another way is this formula, degree of freedom is nd minus k, and one is that number of coordinate and minus number of constraint equation. Now what will happen if the coordinates are not independent? So if coordinates are not independent, so what we will do, we have to make them independent. Okay, so that method is called Lagrange undetermined method of undetermined, Lagrange method of undetermined multiplier. Undetermined multiplier. Okay, so these are just basics of Lagrangian dynamics. So main Lagrangian will come next. Okay, so next concept is types of constraint. Okay, so we know that types of constraints. So constraint means limitation on the motion of object. Okay, so first type is called holonomic constraint. Holonomic constraint. Okay, so if there exists, so if we can find out the algebraic relation between the coordinates, okay, then this constraint is called holonomic. Okay, so let us take one example. That's there is a sphere Okay, like this. Here is x, here is y, here is z direction, and here is a one point particle p. Okay, so in spherical coordinate system we know that here is origin, we take center as origin, we join this point and we call it as r. Okay, and the angle from the z axis to here is theta, and here is one angle that is called the, we take projection of this point on this plane or this circle. Okay, this circle will be actually, let me make it again. Okay, so here is x, here is y, here is z, and here is a sphere. Okay, and this is a center of sphere. So let us, here is some point P on the surface of sphere. So to describe the position of this particle, what I will do, I will connect this point origin and this position, and that is called the r. Okay, and the angle made by this position vector r with z axis, from z axis, is called the theta. Okay, now because this is a 3 dimension, what I will do, I will take the projection of this particle on this circle. So if I draw the here, so that will come out here, because it is in 3D, so it is little bit difficult to explain in 2D in 2D space. Okay, so here is, and we connect here. This is, for example, this is rho. Okay, so this rho will make angle phi. Okay, so this is a rho, this rho will make angle phi with x axis, which is called the azimuthal angle. Okay, so for example, this is making some plane, here it is also rho. Okay, so it is plane, so what I will do, for example, this is a z axis. Okay, so here is a center, this is a position of the particle, and this angle is theta. So let us suppose this is starting from here, this position is starting from here, so it is here, then it is here, then it is here, and let us move this pi angle. Okay, so it will trace out like this. Okay, okay, so because radius are equal, like this. Okay, so this is a theta. So what happen, इसको थोड़ा सा छोटा कर देते हैं, like this. Okay, so this is theta. So if I move this vector from this axis, from here z to like this pi, then it will be make a semi circle disk. And if I rotate this disk along this x axis with angle 2 pi, so it will trace the this whole surface of the sphere. Okay, so that is here idea. So now we know that position of this r can be written as directly, that is x square, equation of the sphere is x square plus y square plus z square is equal to r square. Okay, so in this system the relation between coordinate system can be described in the form of the algebraic equation. Okay, because here is equal to sign. Okay, so this is algebraic equation. So this constraint is called the holonomic constraint. Holonomic constraint. Okay, so another type of constraint is non-holonomic. Non-holonomic constraint. Okay, so let us take one example. So in non-holonomic constraint, if there exists inequality between coordinates, okay, or if there exists inequality between the coordinates or constraint relation. Okay, so then that constraint is called the non-holonomic constraint. Okay, so let's take another example. Let's suppose there is a carom board. Okay, so the example of carom board, that is there is x, here is y, and this is a carom board. Here, these are the holes, and let's suppose we have a striker at this, okay, striker at this center. Okay, so this is x. So now if I want to represent that what is the position, what is the limit of x and y, so what can be that limit can be written in this way. For example, x can be from, if I take here 0 to some value of x. Okay, so okay, so value of x will be 0 less than or equal to 0 to, let us some value x, capital X. Okay, and value of y, if this is a let us suppose it is a L. Okay, L and L, so that L, and similarly for y. So this motion is this motion is limited in this space by these two equations. So these are inequality equation. Okay, so that is x can be 0 to L and y can be 0 to L. Okay, so these constraints are called the non-holonomic constraints. Okay, so now let's discuss another type. Okay, so these two types of the constraints are further classified as a subtype of the constraint, or that is called the first one is scleronomic constraint. Okay, ronomic. What is pronunciation of this? I don't know. Scleronomic constraint. So in scleronomic constraint there is constraint relation in it, constraint relation okay, contain time explicitly, time explicitly means in the equation there is a time, the time is visible in the equation, so that equation is called the scleronomic equation and rheonomic equation. Another subtype is rheonomic constraint. So in this type of constraint it does not contain the time explicitly, does not contain okay time explicitly. So let us take example of these two types explicitly. Okay, so this rheonomic constraint, there is, we have discussed this example here. So this constraint equation is rheonomic because there is in this equation there is not a time. Okay, so this equation do not depend on the time explicitly. Okay, here is no time. For example, x square plus y square and plus t square, time is not visible in this equation simply. Okay, so let's take another example of scleronomic constraint. Okay, so for example, let us take, this is x axis, this is y axis, and this is z axis, and here is a sphere. Okay, it is a center O. Okay, so this is a rough diagram actually. Okay, and let us suppose that here is some point which is actually, here is some object placed on this sphere. Okay, okay, so coordinate of this point here, actually the coordinate of this particle here is x, y and z. Okay, so this particle is moving along the surface of the sphere. Now what is happening, that after some time we move this sphere along this direction. So after some time t, this sphere is at this position. Okay, here like this. Oh, here it is very bad. Okay, so let me select from figure from here, shape. Okay, so it is, arey yaar, let me erase. Okay, so like this. Okay, so ignore this actually. Here is. So now this point will be at some another coordinate system. Okay, so x coordinate of this after time t, let us suppose this distance from this origin to here, this origin. अरे यार ये कैसे होगा, रहने दो इसको. Okay, so this, if it is moving with velocity v, then this distance will be equal to v into t. Okay, so x coordinate will here. Okay, correct. Okay, so x coordinate here is 0 at this point. X coordinate is 0 in this, along this direction. Y coordinate is vt and z coordinate is 0. Okay, at this position. Okay, so now if I have to write the coordinate of this point here, because this particle is moving, after some time this particle reach at here. Okay, so x minus, so constraint equation will be equal to x square plus y minus vt square plus z square, and that is equal to r square. Here is, this is r. So position at this point 0, I have written here. Okay, 0 vt and 0. Okay, so initial minus final. Okay, so x square plus y minus vt square and plus z square is equal to r. So in this equation there is time explicitly. Okay, so it contains time explicitly. So this is holonomic and rheonomic constraint. Okay, okay, so this is a holonomic and rheonomic constraint. Okay, so these are the two example of holonomic, non-holonomic and rheonomic and scleronomic constraints. Correct? Okay, so as I have discussed before, that if I want to know the position of the particle after some time t, for example, here is some particle. Okay, at x is equal to 0, here is some particle at origin. Okay, and after some time it is moving here along this line, and after some time t it reach at this x. So now if I want to know what is the position at this point, okay, if I want to know what is the position of this particle after some time t, okay, after some time t here at x, then it is also important to know that what is the initial velocity of that particle. Okay, so what will be the velocity? So to predict the dynamics of the particle, to know the position and velocity, both are important. So now we will discuss about the generalized velocity. Okay, so generalized velocity are the simply total derivatives of generalized coordinates. Okay, so that's for example, if qi is the generalized coordinates, then qi dot will represent the generalized velocity. Okay, so that is it. So now there is a concept that generalized coordinate are independent to each other. Okay, they are not dependent. So we can write here delta qi by delta qj, that will be equal to chronicle delta ij. Okay, so which can be further equal to 1 when I is equal to j, and 0 when I will not equal to j. Okay, so let's take example. Okay, let's take simple example that how this is possible. So we are assuming actually that generalized coordinates are independent to each other. They are not depending on each other. Okay, this is assumption in Lagrangian assumption. Okay, so if in Cartesian coordinate system we have a three kind, that x, y, z. Okay, so let us take this as a 1, this as 2, this as 3. So q1 is equal to x, okay, and q2 is equal to y, and q3 is equal to z. Okay, so what I will do, if I take q1, for example, delta of q1 by delta of q1, so that is delta of curly by x, okay, delta of x divided by delta of x, because q1 is x, so x and x will equal to 1. Okay, or if I will calculate delta q1 divided by delta q2, okay, so that is delta x divided by delta y. So the differentiation, the partial derivative of x with respect to y will equal to 0, because they are not depending on each other, so that's 0. Okay, so in this case, when 1 and 1, this I and j, okay, from here I and j are equal, 1 and 1, then it is coming out to 1, and when they are different, 1 and 2, then it is coming out to 0. Okay, similarly generalized velocities are also independent to each other. Okay, so that is delta q I dot by delta q j dot is equal to 0. Okay, and generalized coordinate and generalized velocity are also independent to each other. Okay, so what it means, that delta qi by delta qj dot is equal to 0. That means the partial derivative of the generalized coordinate with respect to the generalized velocity is 0, or vice versa. We can write also in different way. Correct. So we need these all fundamental things to study the Lagrangian dynamics. Now we will come to the Lagrangian. So that is the main topic of today, that is Lagrangian. Okay. So what is Lagrangian? Okay, so I will take 10 minutes and I will discuss this, and then we will stop the class. So we know that there was a question that, let us suppose x and y. Okay, so if I have a 2 points point A and point B. Okay. So here is origin. So we can move from A to B by a different path. Let us suppose one person is moving along this path, one is moving along this path, and one is moving along a straight path. So the question is that along which path a particle should move from A to B so that it will take a least time. Okay, it will reach at first. For example, there is a 3 person. Let's take they are moving from one point to point A to B in 3 different paths. This is 1, 2, and 3. Okay. So which person will we reach here first? Or we can say that what is the shortest path between A and B? So that was question in the mathematics. Shortest path between A and B. Okay. Shortest path between A and B. So now what we will do here, that shortest path between A and B. So in mathematics what we will do, we define some functional, that is called, what is functional? Functional is some function of function. Okay. So this function, so what we will do, we minimize this function along this path. So what we will do, we take a change delta of this function and we put it is equal to 0. Okay. So shortest path will be those paths along which this functional f will be extremum. Okay. So when we solve this equation, when we solve this equation in mathematics, so we get Euler equation, that is this by curly y x is equal to 0. Let me check. Okay, dy dt. No, it is not equation. Let me. Okay, so Euler solved this problem. Euler solve it. Okay, so what he found, actually he take dy dt by some function, that is delta f with respect to delta x dot minus delta f, okay, by delta x is equal to 0. Okay, if x and t are the variable. So Lagrangian was the physicist who actually replaced this functional is equal to some function L, which is a function of q dot and t, and this function is called the Lagrangian. Okay. So this Lagrangian is a function of q dot and time. Okay. Okay, so when we solve that variation principle, that is called the how to find the shortest path, that is actually called a variational principle. Okay, variational principle. So what we do, we take variation of that function delta f is equal to 0. So when we use this variation method for this function, then we get equation of motion, and that is called delta dy dt delta L by delta q dot I, okay, minus delta L by delta qi. Okay, here is no dot, which is equal to 0. Okay, so this equation will called Lagrange equation. Lagrange's equation. Okay, so in Lagrangian dynamics, instead of using the Newton laws of motion, we will use this equation. Okay, this is called the Lagrange equation. Okay, thank you.